This recording brought to you by the University of Adelaide.
Thank you very much. It's my great pleasure, my wife Gillian also, to be back in Adelaide, a place of which we have many fond memories, and it's my great pleasure to be able to speak today. I'll be talking a great deal about John Carver's work, who did most of the space physics here. It's my great pleasure to know that Molly and young John are here as well. But now I'm just going to reminisce about the science that we were doing. The space science was something quite new to the scientists of the world, really. It was science that you did in a huge hurry. You had enormous risks. You had very black moments when, after 6 months of work, something blew up on the launch pad and in 1 second the whole thing was gone. So there's this sort of new background to physics that we all had to learn about on the job. Next slide, please. Of course, it all started. The younger people will not even recognise what this is, perhaps. The older people will remember Sputnik 1. Launched by the Russians at the time that the Americans were terribly confident that their Vanguard spacecraft would be the first satellite to be launched. Their choice of the name Vanguard was unfortunate. To give you a feel for the times, we Australians used to call it Project Guardvan. And the younger people will not remember that the last carriage on a train was always the guard van. The Americans found this not very funny. But anyway, so next slide, please. Now, so the space era started, and at that time, Adelaide really had a marvellous opportunity to be able to be involved in space. And I have up there the reasons why this was the ideal place to come to. Nearby was the Weapons Research Establishment, established somewhere from memory about 1947. There was the UK-Australia joint project. WRE was part of that. Then there was the Woomera rocket range, which was a marvellous rocket range. Over land, many rocket ranges, the payloads fell into the sea and you lost them. Here in Australia, the rocket could go 2,000 kilometres and you'd still get the payload back. Maybe not in one piece. But so here we had this marvellous opportunity. But the problem was WRE was really developing the British intercontinental ballistic missile, the Blue Streak, and other rockets. And so while in other parts of the world, university community was welcomed into space, we were not that well welcomed in Australia. And this is where John Carver achieved what I regard was almost a totally impossible thing. Very much, I believe, with the encouragement and mentorship probably of Marcus Oliphant, and Oliphant probably acting very much as an advocate in other circles. John liaised with the head of the Department of Supply who ran Woomera and with the chief scientist there, with the net result that Adelaide was able to enter into exploration of space with small rockets. Next slide, please. We'll talk about the blues later. So here's one of the small rockets that were used in that era. These were locally built rockets, these ones. These were called Hat, Cockatoo, Long Tom. They had one characteristic. They took off with one hell of a rush. And I was told today that the shock gravitational force was 30 G. Now, we all used to build our own electronics then. And one of the real hazards of being a experimenter was building experiments from electronics, and to have them withstand 30G was a bigger challenge too. But anyway, these were some of the things that we had to face with as space scientists. Shock, sudden evacuation, all these things which will, you get 5 minutes of data if you're lucky. The telemetry system that sends the data back to Earth might fail. And it was a very hazardous place to work. There was a saying back in the early days of space, you've got to be mad to be a space scientist, but if you're not when you start, you soon will be. And there was a certain truth to this. Next slide, please. So this is one of John Carver's ultraviolet rockets. Now, John took a very wise move. In view of all this risk, he said, we must have both the space program doing things which have never been done before, and also a laboratory program which there's a reasonable degree of surety we can do top-class physics, which is highly publishable. And so he chose to go into atomic spectra in the ultraviolet and other things like that. So that was the backup to the rocket program. Next slide, please. And this is one example of the work that John and his students did. At this time, bear in mind we're talking of the early 60s. This work is, some of this is a bit later, I'm sorry, but the earlier rocket flights were in the 60s. We knew very little about the way the atmosphere was constructed. We knew very little about how it changed during magnetic storms. And so John's rocket program directed to that, measuring the ultraviolet reflectivity of the moon and so on. Every rocket was a pioneering measurement of a new area. And this is what kept us going. You might, I wasn't of course involved in this, but I talk of the space community in general. There were terrible risks, but you were almost guaranteed something highly publishable if it worked. And that's a great challenge. Next slide, please. And then one day, from memory at the end of 1966, John got an offer. And the good news was that the United States, which had been firing rockets out of Woomera to test the nose cones. This was for re-entry to find out whether the nose cones would burn up on re-entry. And they'd brought out a number of Redstone rockets. The Redstone was in fact an American souped up V2, and the V2 was the rocket that Wernher von Braun and his friends rained on London at the end of the war. So here we were with a V2 that was left over, a Redstone, and the Americans had been told you must take it home, anything that's left over, and they said, no, we'll give it to you and we'll launch it for you. And that's the really good news. The bad news was it has to be launched in 11 months. Now, nowadays it takes about 10 years to build a satellite. I think the record was by another Australian, Brian O'Brien, who built one in 4 months. But 11 months, but he had a lot of big start. Going from scratch to a flight which would have to go, there was no delays possible, in 11 months was a real challenge. And next slide, please. There it is, that's RESAT, as it was called, the Weapons Research Establishment Satellite. And all the people who were involved in getting it there. Next slide, please. This is from the paper, quoted there, shows RESAT in orbit, spinning around the, that axis, scanning the sky, and the object of the exercise was to measure the absorption of sunlight as the satellite went from dark into daylight. And so measuring the absorption characteristics in the ultraviolet. Next slide, please. This is one of the results from the paper, a paper that was published based on that data. You can see reference to the RESAT measurements are here, and this gave added to very good information that we had on the properties of the sun in the ultraviolet. Next slide, please. I mentioned that there was a fallback side of the program, and this was to use monochromators to measure the absorption and other properties of atoms in various absorption bands. This is one of the monochromators that was used. And the program, next please, these results had a very good impact factor around the world. This was a very clever way of making sure that in addition to the observations with the satellites and rockets, that there would be data which was valuable to other experimenters worldwide. And these papers and others, based on that laboratory work, had extremely good impact factors, citation rates, which extends to until today. Next slide, please. I throw this in. I didn't know whether there'd be any mention of Fred Jacker and the Mawson Institute. Graham Elford mentioned it. I won't say any more other than to say that's another image of a laser sounder operating in Antarctica. Next, please. So now we move to another part of space in those days. Rockets were a terrible way to live, and satellites were a little better. And for graduate students, it was almost impossible to train them unless you did terrible things to graduate students, that I tended to do. Balloons were much better. They gave you a gentle ride. They were a lot cheaper. You got the thing back with any luck. We dropped our package onto a beach somewhere down near Port Adelaide, and the balloon itself, about 10 acres of plastic, landed in the Port Adelaide Channel, and the balloon launchers told me, and I used to talk to the radio a bit, they said, just disappear. Don't talk to anyone until we sort that one out. But anyway, so balloons. It took you up to above 99% of the atmosphere and gave you a very nice platform if you could measure things in that part of the atmosphere. Luckily, just 3 years, no, luckily in 1962, Bruno Rossi, who'd been my mentor, he and his colleagues, Giacconi, we'll talk of him again, had discovered that stars emitted X-rays. The theoreticians had always said this was totally impossible. Black body radiation will certainly not give you any noticeable X-ray emissions that we would see at Earth. So Bruno and his friends found them. By 1964, I had flown a balloon from India, and we discovered high energy photons from a couple of sources. I brought that package to Australia. We flew it from Waikari. One very cold night, the balloon leaked and we got nothing. But anyway, we started in 1966 on a new program. Next slide, please. This is the way you built instruments for balloons. The general term was, it's a rat nest. They were not terribly well built, but they worked. Next, please. This is a X-ray observatory that we built for use to fly from Mildura. We had two separate telescopes. The best one with lots of scintillators, and that thing over there is the heart of it, with an addition on to make it even have a finer focus, and another one somewhat bigger, but without so much suppression of noise. But both of them pointing the same direction, and by radio we can control them to scan back and forth across known parts of the sky that we thought we were interested in. Next, please. This is what it looked like at launch. Balloon there, kept held down. This thing will take off and lift about 1,000 pounds, 500 kilos, in a bit of a snap lift. Here's the observatory. That's a rotating motor that we turned the observatory relative to the very large angular momentum of the balloon itself. And radio communication to send all our data back. Next slide, please. This is the result that we obtained, or some of the results. These were quite pioneering at the time because no one was flying satellites yet that could measure photon energies up around about 60 keV. 60 keV came into the atmosphere to our depth very nicely, and we were able to, because at the time the theoreticians were now very keen to explain that stars could really make X-rays, and the spectra going from 3 keV to up to 60 keV was very useful for the theories. So here we are measuring quite well with this observatory. Next slide, please. But now, also, up at Urma, there was this quite beautiful rocket called the Skylark. And there were a number being flown each year with no payloads. Seems ridiculous. And the problem was Australian scientists had never been able to get to use them, and John Carver's agreement did not continue or include the Skylarks. A colleague of mine from the University of Tasmania and I solved it the following way. We had a conference in London, Cosmic Ray Conference. We went to the British equivalent of NASA. And back in those days, our passports, we Australians had British passports. On the front, it said British passport. And inside, citizen of Australia. So I went in and said, look, we're British. The universities of Adelaide and Tasmania want to fly on the Skylarks, not as Australians, but as British universities. And of course they laughed and rolled on the floor as if to say, what will these stupid Australians do next? And they said, write us a proposal. I wrote it overnight, took it back in the next day, and they said, we'll give you an answer soon. They did the next day. Next slide. So the universities of Adelaide and Tasmania, very quickly, with a few things that had fallen off the back of a NASA truck, was building. Now, where was the other one? The little hads and hats and cockadoos were 10 centimetres in diameter. These are 40 centimetres. This is a great thing to build your instrument into. These are the X-ray detectors with Venetian blinds to define their field of view. So any star up and down there will be seen there, but it will then be seen here at a different time depending on its declination and so on. Next slide, please. So we had 2 flights in April 67, and from the Northern Hemisphere, Bruno Rossi and his colleagues had seen Sagittarius and Scorpius XR1. We'd always joked, maybe we'll see an X-ray star in the Southern Cross. So we analysed the data, and we could see we had something new, no one had seen before. and the stupid thing kept appearing in the Southern Cross. Now, a scientist dreads a self-fulfilling wish. And here we were with this thing would not move. Nothing we did would move it out of the southern, the vicinity or the constellation Cruxus. And so we flew another flight 2.5 weeks later. Still there. So that was it. We had discovered what we had thought we would, and were very worried that we had done so. What we also realised very quickly was that this source was changing in its intensity. About 10 days after that flight, I was giving a lecture at the American Institute of Physics, APS, American Physical Society meeting in Washington. And I used all this. And Riccardo Giacconi, who later got the Nobel Prize for X-ray astronomy, leant across to Walter Lewin, who incidentally has signed that over there. Walter was a well-known X-ray astronomer from MIT, and Lewin, in his reminiscences of early X-ray astronomy, says this: one of the most exciting moments was when we showed this slide, and Giacconi leaned over to him and said, "Walter, do you believe this rubbish?" And that's a fair indication of what science like was in those go-getting days of space. Now I have to hurry. Next slide, please. Now, just to show you, though, what can go wrong. We then got more flights on Skylarks. We got cheeky. We started to build big ones. This was our biggest one. This is, for that time, it was about 300 times bigger in cross-section area than anything ever flown up till then. And if it had got there, we would have made a marvellous measurement. And you can gather something went wrong. It did. Next slide. So here it is. We're putting it in. Well, everything had to be tested in vacuum. And so here we have Ian Toohey and Barney Barndon, Roger Francis from the University of Tasmania, putting it in. So we go up and light the blue paper, and blew up on the launch pad, and that was the end of that. And we never got an opportunity to do that again. Next slide, please. Now, in parallel with all this, we were getting data back from a series of satellites I had launched. Well, the first one was launched the year I came to Adelaide. And there were 7 of them, one after the other, for the next 4 years. In this day and age, the idea that one experimenter could have 7 spacecraft in a period of 4 years, the mind boggles. But anyway, here it was. It was called a bargain basement satellite. It would go out to the orbits of Mars and Venus. Next slide. It would measure cosmic rays as they came into this aperture and were counted back there. Next, please. By 1969, we were in the most incredibly, the sort of situation we could never, ever have believed we might encounter. Here we are looking down on the solar system from up at the celestial pole, say, ecliptic pole. There's the sun, here's the Earth. We have spacecraft spread out, 4 of them around the sun. This one's 250 million kilometres from Earth. Radio signals are coming back from all of them to Earth. So we are able to look at what's happening in the solar system as explosions, solar flares and things like that happen on the sun. Next, please. We found out that there were lots of strange things in space. Comparing the flow of the cosmic rays with the magnetic fields being measured by the spacecraft, we learnt that the cosmic rays weren't just coming out along what's known as the Parker spiral field. they were wiggling back and forwards. We called it the wet spaghetti model because we had discovered this as we were going to lunch, and there happened to be spaghetti bolognese on lunch in the cafeteria. You can have some fun in science. But anyway, next slide. And this, bear in mind, these spacecraft were flown with the main purpose wasn't science. It was to protect the lives and the virility of the astronauts going to the moon. Because the radiation was thought to do quite bad things to both all of them. So the question was, if there's a great explosion of radiation on the sun, how much of it, if it's on the back side of the sun, how much will get to a satellite or an astronaut on the moon? We knew that there would be a great attenuation around the solar system, but this gave us the ability to measure it for the first time ever. And you can understand, so here we are with two of the spacecraft, the two near Earth. We're getting a good record of the very great intensity increase. But what we see is out there, up there, was 3 orders of magnitude more intense. And this told us a great deal about how to make sure the astronauts were not killed when they went to the moon. And that was the applied part of my research. Next slide, please. Our version of what John Carver did, namely having a backup program, was we had a number of analytical and data processing or data analysis projects that were going on in parallel. And these were basically extraordinarily successful. We had Ian Urch was working with a theoretician, or would he be no, he was an applied mathematician, so I guess he's an applied, I don't know what he is. Anyway, Leo Gleason and Ian did some work which is of major importance now in studying the way that the cosmic radiation varies with time. Barney, or Leighton Barnden, whose experiment we saw blew up, he did some work which is still cited today on the nature of the shock waves that come out from the sun when a flare goes off. And one of our other students, Ian Palmer, became very much an expert on the nature of the energetic particles that emanate from the sun. So that is the story of both the John Carver's program and my program in those exciting years. The years before big satellites began to take over all the things that rockets did. Rockets were quick, balloons were quick. You could do things, and we defined the program which basically the satellites then took over. And so it was a stimulating time, a risky time. So let's have the next slide, please. And that just really summarises it. John Carver's program number 1 and 2, very deep, because I simply don't know how many rockets they flew. It would be in that more than 10, I'm sure. Many observations of the structure of the atmosphere and in various wavelengths of the ultraviolet spectrum. The backup or the parallel program to have assured data output, scientific output. Our activities in X-ray, particularly X-ray astronomy, and our backup program to make sure that there were things, if those all blew up, that we would have some good scientific output in another area. Next slide, please. And thank you for letting me, shall we say, share with you our memories, my memories of a very exciting time in physics and in astronomy. Thank you.